just start now.
Okay.
Okay, and then I think it's raining day, so maybe some people will come in later. And welcome to our IPCS faculty lecture series. This is our third and our last invited speakers in the IPCS lecture series in this semester. And the topic will be the development of earthquake early warning system. That is the most important, from my view, is really life-saving technology to many earthquake-prone disaster countries. And that is actually very beginning from Taiwan. And the disaster developer and then the innovators is Professor Wu Yiming. He is also the director of the Geosciences Department. Let's welcome him. And he is also our IPCS members. And let me also take this opportunity to introduce these all students to Professor Wu. And I think most of you are, except you, right? Except you, others are our IPCS students. You are, Max is from, maybe each one introduce yourself to very briefly to the Professor Wu.
I'm Max, I'm from Haiti. I'm PhD student.
Haiti. And then?
Barry from Australia.
Barry from Australia.
Yuan from Vietnam.
Yuan from Vietnam.
Yuan from Colombia.
Colombia.
You are our department. Yes.
Okay, you're the department. And then?
Joe from Taipei.
And say something about to introduce yourself to the Professor Wu.
I'm just student.
Okay, continue.
Hi, I'm IPCS student.
And you want to be interested in that, in oceanology or in something else?
Yes, I'm doing. I think we've met. No, we haven't met before. but most of the time, do you know the PPP in your department? It's like at Wednesday night, and we have
Okay. Rivers.
Yeah,
rivers. Yeah.
Professor Wei.
Okay. Very briefly, quick.
I'm Yang Sisen.
Okay.
I'm now studying with Professor Joe from Geography department.
Okay.
I'm Li IPCS student, studying with Professor Joe in forest.
Forest department.
It's Kevin. I'm a PhD at IPCS. My research interested in is in coastal climate adaptation.
Coastal climate adaptation.
IPCS PhD student, topic focus on the international cooperation of natural disaster and humanitarian relief.
Okay, thanks.
Okay, your time.
Okay. I'll talk about the earthquake early warning, and here the major topic is using the low-cost sensor. So in the past, for the earthquake early warning, they always use a traditional instrument, so pretty expensive. For example, maybe there more than 1 million NPD in Taiwan here. But because of the observation, the recently changed a lot. We try to use the low-cost sensor. The low-cost is mean that just you can use the main sensor, maybe several US dollar to tens of US dollar to hundreds of US dollar. This is so-called the low-cost. But the concept will change a lot. In the past, you need to buy the expense instrument. You just can deploy it at some station. But recently, the observation a little bit changes due to the using low cost. So we can operate it in dense array. Then they will change the observation. So what is why Taiwan want to work on the earthquake early warning? It's due to the 1986. An earthquake occurred in Hualien. So earthquake occurred in Hualien, but this earthquake caused serious server damage in Taipei City. It caused the few buildings collapsed that killed lots of people. You know, in Taiwan, last few weeks, you also feel the shaking from the bottom. This year, earthquake occurred here. He wave propagated to the Taipei City in about more than 15 seconds. But the shear wave propagated from here to here more than 30 seconds. You know, when earthquake just occurred, produce shear wave and the P wave. P wave propagated more fast than shear wave. But for earthquake, the major energy carried by shear wave. So for this case, earthquake occurring here, in case we can have a small array located here, seismic network located here, can detect the earthquake and report the location and the magnitude less than 15 seconds. You can have more than 15 seconds of early warning time before the shear wave in Taipei. So this is why Taiwan start to build up the early warning system. Because Taiwan start to develop the early warning system around 1994. Already start to develop the early warning system. So what is the earthquake early warning? So try to, before the strong ground motion, there is a focus on the predict the shaking. And another we so-called the earthquake rapid reporting system is before the damage is discovered. Generally, when earthquake just occurred, it caused the damage. But the disaster manager do not know where is the damage area. So at that time, you need to have the rapid reporting system. Although earthquake occurred, but you focus on the reported shakemap. So-called shakemap is the shaking condition of the ground. This is to predict the damage. This is a little bit. For the early warning is to predict the shaking, but here is to predict the damage. So focus on the seismic rescue efforts. And for earthquake early warning, you can separate the regional warning and the on-site warning. I will introduce, for example, an earthquake occurred, it produced heat wave, shear wave. So in case you have the instrument that close to the source area, you detect the earthquake source, epicenter and the location and the magnitude. Then you can predict the surrounding ground shaking. So give the warning to outside the source area. This is so-called the regional warning. So regional warning is it detects the earthquake epicenter and the magnitude, and for the warning for the region is the outside the epicenter area. And another so-called is on-site early warning is you want to protect this target. So you put the detector close to your protected target. You can be one station or small array. When you detect the P wave, receive the P wave, try to predict the shear wave amplitude. This is the so-called on-site warning. So Taiwan developed the early warning system for more than 25 years. So I guess it's a very successful case in Taiwan is for the 1999 the Chichi earthquake, the moment magnitude 7.6, and about 2 minutes, our system can report the magnitude and shakemap to public about 2 minutes. This is very important due to the rescue the team know where is the damage area. Before this is 1999. Before the 1999, I guess the most significant earthquake is the 1994, January 23. I guess it's January 23. North Ridge in South California. It also, at that time, the responsibility agencies, Caltech and the USGS, it took several hours to report the hypocenter. That day, you know, the several hours delay for the rescue effort, it caused a lot of cost. And 1 year after, just after the North Ridge earthquake is in Japan, Kobe. This is an earthquake occurred in the Kobe, and the president of the Japan government, he watched the television, you know, several hours, also where the earthquake occurred. I guess this is at that time in Taiwan, this achievement is very important. I guess for the North Ridge earthquake, I guess it's one name, the so-called the earthquake produced the bright rust. So this is the first proposed bright rust. And in the actually 2002, the Central Bureau of Taiwan already can report the earthquake information about 20 seconds after the earthquake occurs. That time, I guess, is the most the best early warning system in the world. But at that time, the Central Weather Bureau do not use this information. Due to the want to issue the warning, you need to take the responsibility. This is very important. So this is for the seismogram of the GG earthquake. This is Sun Lake, the station here. So earthquake just occurred. This is 0 is the earthquake occurred about 22 seconds here. So in the Sun Lake, maybe the larger station already passed. Even the Taichung, already maybe caused the damage. But just like 22 seconds, the P wave did not propagate into the Taipei basin, so we have a longer time for warming. But currently, Central Weather Bureau improved a lot. Now, Central Bureau can issue the report the early warning message or alert around the 15 to 20 seconds. So, in case the earthquake occurred in Hualien, not Taipei, you can receive the alert, the message from your mobile phone. I guess the last 2 weeks when the earthquake occurred in Hualien, you already received the. In case you was in Taipei, you will receive the warning. So for the on-site regional warning and the on-site warning. For the regional warning, generally it takes about 15 to 20 seconds to locate the earthquake. So around this circle, you may not have the warning, but outside of this circle, you have the different warning time. For example, if the earthquake, for example, the GG earthquake occurring here, 20 seconds, the shear wave propagate here. So, and the shear wave needed propagate to the Taipei city. Here, you may have the 20-second warning time for Taipei city. This is for regional warning. You can give warning for this outside this circle. But for the regional warning, you cannot provide a warning within this circle. This circle we so-called blind zone for the early warning. So how to solve this problem? You need to use so-called on-site warning. On-site warning is mean that this is a seismogram, this is acceleration, this is velocity, this is displacement. I know a little bit harder for you guys, for some people. Acceleration integrate into the velocity integrate to the displacement. So even this is very close to the epicenter area. When earthquake just occurred, the shaking is small. So in case you can use the early portion of the P wave, try to find the relationship between the peak ground velocity or peak ground acceleration. So then you can have the few second early warning, and this is so-called onsite warning. So in this method, we will propose just use PB method. This is a vertical displacement. Simply just a vertical displacement. Try to figure to define the relationship between the peak ground velocity, which is the largest the entity. So we try to use this. Generally, in our study for the case, the vertical displacement larger than 0.5 centimeter, here the following shaking may cause the damage. So for this case, in case you detect the vertical displacement larger than 0.5 centimeter, then you may have a few seconds before the peak ground velocity. So this is we are seismologists. We learned we got a lesson from the damage of the earthquake. So this is show the damage rate. This is the star show the damage rate. The damage rate is mean the earthquake occurred, then within 5 kilometers, in case the building caused damage, we will assume this is a damage rate. And the blue is a non-damage rate. Generally, I will not use the fatality. Due to the, in Taiwan, the Taiwan earthquake occurred will cause the rock fall. Small earthquake also cause the rock fall, and the rock hit the people, will kill the people. So while I assume the damage rate is using the building cause the building the damage. So you will find that this PD is so-called the vertical displacement from the initial 3 seconds. And you can see the damage records are located here. This is a peak ground displacement. It's the largest entity of the shaking. You will find the 0.5 centimeters. You can separate damage rate and the non-damage rate. Overall, it should be fine, but you still have some. This is so-called misalarm, and you also have a few false alarm. But in this case, you can use this information, then you can do the early warning. So this is another. This is a peak ground velocity is the peak entity of the seismogram. This is the vertical displacement. So we gathered the data from Taiwan, South California, and Japan. We found that this is a non-linear the relationship. So based on this relationship, you can predict the following shaking using the initial 3 seconds of the vertical displacement. So because this is very important. So in case this case, this is 2007 in Japan Noto event, the 0.5 centimeter, in case you reach 0.5 centimeter, you issue alarm. Generally, you can, for some case, you can issue the warning just about 0.5 second after the peak arrival. So the warning can be issued pretty fast. So we do analysis, but you want to achieve the early warning, you not only for the observation, you need an instrument. So this is why about 15 years ago, I already studied the mass acceleration sensor. This is a cheap device. So in case just like the seismometer, in case you can build up like a TV or just like a computer, then you can install to every building, to every family to protect your family. So I started to combine the MEMS sensor and the P-wave method. So just we made this so-called P alert. P alert is a P-wave alert system. This is pretty small, just like this size, made by using MEMS. So for this device, we install to the elementary school or other school. Generally, we have a touch screen to show the intensity or the health condition of the pillar, and this also can provide a 6-hour backup power, and can turn on the sound alert. So for this, just a pillar, just generally for the low down the cost, we use network streaming. The signal can transfer to our server, and we do not use GPS. Similarly, we just use NTP clock due to to low down the cost. Then this can be triggered for the PT or other trigger mechanics. Maybe not so important, but this is supported TCP server and the client. The noise level generally less than 0.1 Gauge. It can be intensity meter or so-called seismic switch. So seismic switch is when the ground reaches some shaking, then it turn on the switch. For this device, we can have the two switch. One we will set up around the 0.15 centimeter, that is so-called watch force. That is the you will watch following shaking may cause the damage, but may not. But in case the PD larger than 0.35 centimeter, you will give the warning alert. This is what we try to design for. Yeah, and this cost is just 1 of 10 of the regular accelerometer. So all the concept of the early warning network system is the Earth occurred in here in case of vertical peak ground velocity larger than 0.35 centimeter. Give warning for onsite. But all of the signal transfer to our headquarters. Then, in case it's large enough, we can trigger another pillar device, and it can be disarm the emergency response. This is all the concept of try to do. So, supported by the Ministry of Science and Technology about 10 years, our group already installed the 695 stations around of the Taiwan. Major install to the elementary school. Why? Why try to do the install to the elementary school? I guess for the disaster education, this is very important due to when you are young, your child, then you know that this device, then the disaster prevention will go to your minds forever. And this is also very important due to the pillar device is two-way. So we also can send information from our center to trigger the pillar device. In case the school want to do the drill, that will be easy to do it. And I needed to tell you this, we install the instrument to the school, also to try to lower down the cost. Usually in Taiwan, every elementary school, they have power. They also provide the internet connection. So we can pretty easy to build up the real-time network. This is around the 700 station all real-time. So you know all of the signal coming to our lab for 24 hours. And in our lab, we just use 3 steps, 2.5 steps to maintain all of the system, include the developing the other extra function. So this is the pillar in the side, and through the socket, the signal transfer. We use the Earthphone. This is a platform developed by USGS, then we can do the earthquake location. We also can do provide the shakemap. I guess this for the early warning portion, this is we can provide the earthquake location and magnitude about 15 seconds after the earthquake occurs. But for this portion, Central Bureau already did. We just focus on the study. And we have another shared memory. We just do the shakemap. I guess this is also very important. So for earthquake location, for traditional to locate an earthquake, you use a rifle to locate an earthquake, and then you determine the size of the earthquake. It means the use energy. So once your system got the wrong location, you will got a pretty bad magnitude. But in our case, I guess we try to develop the shakemap. This is also very important due to when earthquake just occurred, 1 minute, 1.5 minutes, that will provide the shakemap. Shakemap is very important due to when you provide a shakemap, when earthquake just occurred, you know where is the damage area, and the shaking high shake, the centroid point of the high shaking area, it could be the earthquake, the epicenter, and the shaking area you can convert it to the size of an earthquake. So even just use a low cost sensor, our system still can provide a pretty nice strong ground motion. And 3 years ago, February 6th, an earthquake occurred in this is a so-called Meinong. This is the first report from the Central Bureau. It just shows the intensity 6 in here, and the earthquake occurred epicenter in here, but the Tainan area just showed the intensity 5. In Taiwan, intensity 5 is mean the peak ground acceleration larger than 80 gales, but less than the 250 gales. But actually, when earthquake just occurred, our system already delivered the shakemap like here. From the Central Bureau, the epicenter around here. But our dense array in operation, we found that this area, this is a Tainan city. This area, the shaking is larger than 0.4 G, 400 gale. And this area means this area is 250 gale, 0.25 G. So actually, this is the shakemap, but it's very different than the Central Bureau provide. This also provides a very important information. This means that epicenter in here, but the most damaged area should be around this area. And this is also provide another information we so-called directivity or the rupture information. Earthquake occurred in here. Why? This is a high shaking here. It potentially indicates the earthquake initial rupture in here, but propagated to this direction. This is why caused the high shaking in here. Like a Doppler effect. In case you hear ruptures here, you will have observed a really high shaking in here. For our system, not only deliver the information, use email or other provided to. Now we also provide the shakemap to the social media. Why? I try to do it. This is based on the experience from the 1999 GG earthquake. So the 1999 GG earthquake, when earthquake just occurred, your communication resource still can be used for the few minutes. But for after the few minutes, all of the communication channel may be interrupted. So this is why we developed the real-time ShakingAlarm. Then I put on the social media. Due to you upload your information to the social media. It's just one way to there, and the social media will distribute the information to the public. So I guess this is also pretty good experience to use the social media, not only for the gossip or something. You still can use it in this purpose. I just mentioned the reactivity effect. It's an earthquake, 2013 earthquake. Here you have found the north area have a high shaking. The aftershock distributed in here. But actually, a lot of people afraid the seismologists to show on the seismometer. But I want to let you know, the earthquake occurring here, you will find in the north area, the PGA, the peak ground acceleration, the shaking is really high. But this another area, the shaking is relatively pretty small. It's due to the so-called the reactivity effect or Doppler effect. The earthquake occurring here rupture to the north. So the rupture speed is very close to the shear wave speed. So that your energy will concentrate around the shear wave arrival. So you have a high shaking in this direction. But you will find that this energy not so concentrated. It's due to the airspace source move this direction. So this the shaking in the south area is less. So another case for the Meinong earthquake, the same situation. Here, really high shaking in the north west area for the Meinong earthquake. Generally, why the Meinong earthquake, the epicenter located in the Kaohsiung, but why Hainan have a really high shaking? It's due to three effects. One is a so-called the reactivity effect due to the source move to the northwest. This is a so-called reactivity effect or Doppler effect. Another one is a side effect. In the western Taiwan, they have the thick sediment, so it amplifies the shaking. And then another is the radiation pattern. So due to we already built up the real-time system, so we also have the real-time shaking information. In case you visit this website, then you can see these 2 seconds update screen. In case the earthquake just occurred, you can see the seismic wave propagated from the epicenter to the other area. So let's just show the movie. This is 3 times speed than regular speed. So the Meinong earthquake, you will find the high shaking here, back to here. And generally in the western Taiwan, the shaking is much higher than the eastern Taiwan. It's due to the western Taiwan, this is sedimentary area. This is a 1-to-1 speed in earthquake right here. We will find the high shaking move to here. This is due to the rupture reactivity. So generally for seismologists, we will use PGN and the PGV. Generally, this is peak ground velocity. Peak ground velocity, you will find a small triangle. This is a small triangle, solid triangle, show the school affected by this earthquake. So you can see pretty agree with the PGV shape. So this for the PGA, this is so-called like a triangle, agree with the aftershock. So PGA like the much more agree with the earthquake source. And this PGV also very important. Like here, earthquake occurring here, you will find this circle. This circle is mean the peak ground velocity larger than 17 centimeters per second. You will find the solid squares show the damage built. So for this time Hainan earthquake, the most the structural damage building are located at the peak ground velocity larger than 17 centimeter per second area, and this fully collapsed building located here. So here is on-site early morning. So we will examine how this performs. Generally, the vertical displacement larger than 0.3 centimeter, and we will give warning. And you just see between the PGA how much lead time between the peak ground velocity, peak ground acceleration, and we issue warning. So earthquake occurring here, you can see this station called this peak ground velocity. This is the lead time. Lead time. So the Weiguan building almost here. So you can see around the Weiguan building, this area, basically on-site early warning can provide 6 to 8 seconds lead time. So I guess this is very important. But a little bit 6 to 7, 6 to 8 for the people in the building want to escape a little bit difficult. It's still a little bit difficult. They provide analysis, but I neglect this one. So I just showed you another 1 year ago the Hualien earthquake. So 1 year ago, not a few weeks ago, the earthquake, when earthquake just occurred, I guess this name already on the Facebook. Generally, the information put on the Facebook you got much earlier than email. Much earlier than email. So it's just you will find this is a really high shaking around the 400 data here, and then this the 200 around here. So usually this is a big shaking, and all the Taiwan area feel the shaking. So like here we still provide the PGA. You can see this is about 200 around here. But if you look at the PGV, you will find earthquake occurring here. The PGV in here is larger than 17 here, but actually this is larger than this area is larger than 50 centimeter per second. You know, the PGV 50 centimeter per second, definitely you will cause the damage. You just look at the earthquake occurring here, you have found the active shock in here. So this earthquake occurring here and the rupture to the south side. We can see the PGV, the damaged building are located in this area. This area, the PGV larger than 49 centimeter per second. This is the damage the building distributed around this is the peak ground velocity. You know, this is a little bit different. I just introduced in southwestern Taiwan in Tainan. Generally, structural damaged buildings are at around this region, larger than 17 centimeter per second. But in eastern Taiwan, in Hualien, the damaged buildings are located around the 50 centimeter per second area. This means the building, the quality in Hualien is much better than Western Taiwan. Due to the Hualien, they already have a lot of earthquake in the past. So all the buildings mostly are destroyed due to the historical earthquake. So this is a little bit different. So for this case, still the damaged area, still damaged building around this year, so still have the 6 to 8 lead time before the largest shaking. So simply we like to simply just look at the seismic earthquake occurring here. For this is a different position. You have found this area, the seismogram, this area a little bit different than other areas. Actually, this is the damaged building area. This is so-called kilohertz. This is the peak ground velocity can reach to this is to the 75, 64. I guess here PCV is somewhere can reach to 100. This is why it caused the damage. This is so-called kilohertz. Why this kilohertz? It's due to the earthquake initially occurred in this area, rupture to the south. But beneath the water, they have the one rupture so-called asperity in here. It causes the high shaking beneath the water. So for some people, survivor, they just tell the media reporter. They say, I feel the up and down shaking first. Then the following, I feel the horizontal shaking. But later, I feel the up and down shaking again, then building collapse. How? Generally, you will feel the up and down shaking. It's caused by P wave. Why? P wave coming the later. It's due to the earthquake just rupturing here. It produced the vertical P wave and the S wave. So the survivor here feel that the P wave and the shear wave come from this portion. But later, the earthquake ruptured beneath the water. Because the rupture beneath water, it produced the P wave and the shear wave. So you feel the up and down. So again, so this is due to the earthquake the source characteristic. In the past, the Central Bureau of Taiwan, the director of the seismological research observation center always say this is earthquake occurred. They will say, oh, this is a regular or normal energy release. But I will point out that each seismologist sometimes it's true, is the normal energy release, but then we will talk about why it caused this phenomenon. Okay, so this is a few weeks ago. So in case our system still upload the ShakingAlarm to the Facebook, but they look at this earthquake occurred, the magnitude 6.1. You will see this is really high shaking in here. This could, based on the peak one acceleration, it could be cause the damage. But now our system can provide the PCV map. So also 1 minute, 2 minutes, I got the information from our system. We found that actually for this earthquake, the PCV did not larger than 17 centimeters per second. So I was thinking that at that time, just 1 minute after the earthquake, I know this water earthquake, the damage will be limited. Yeah, this is very important. So based on the PGA, you are thinking, you got the information, you have the earthquake, and you know the 6.1 compared to the 2 years ago, the water earthquake. You would think that it could be caused the damage. But especially for the 2 years ago, the Central Bureau first announced the magnitude for is 6.0, a little bit less than this one. But actually, you compare to the PGV map, you will know the damage is limited. Okay, it's a little bit. Even we use a low-cost sensor, then the double integrate, we can get the co-seismic deformation. The acceleration, velocity, and this means that we can get the co-seismic deformation. So seismic, but you can use it like the GPS. earthquake just occurred, you can know this earthquake. This is a little bit difficult. Even the local sensor, we feel that at some frequency band, you can see the seismic wave aggregate from epicenter to other area. This is a so-called surface wave. You know the observe this wave, you know you can emerge to the ground the rusty structure. So in case you are interested about the PLN network, yeah, you can download near real-time data at this website. It is fully open. Everyone can download the seismic. We are not focused on early warning. I guess now it's very important to move to the structural health monitoring. So now we install the instrument in the building. For the first moment, we give the early warning based on the PWS. But when earthquake passes, then data can be used to the structural health monitoring. I guess it is very important. You are thinking about one high rise. How many, many people work inside, a lot of community inside. You want to expect the people who are just continuously in operation. I guess just use this type of method. You can save a lot of money for the decision maker. Not only we promote the PLN system in Taiwan, we also promote it to other countries. Now we just try to the Bhutan and Nepal and the Myanmar. I guess this area, especially for Myanmar, I guess this is a really high risk area. Okay. So the summary of PLN system is also the on-site. The regional rapid reporting with real-time ShakingAlarm. This is very important. Low cost and easy maintaining, low cost and it could be operate in dense array operation. I guess dense array in operation used in the low cost sensor. Not only limited to the seismic, you also can extend that to other sensors for the low cost sensor. Okay, this is my sharing. Okay, thanks for watching.
We are in Taiwan, so we feel a lot of earthquakes, a lot of experiences, so much a lot of things to ask. The professor will please ask your questions right now. Please. Yeah, Yang, go ahead.
I have a question about, you show a diagram with high correlation and whatnot. I forgot which slide it is, but I think it's pretty easy. Yeah, this one.
Yeah.
Because I think you get a lot of sample as a lot of sites and it is really highly correlated, but I would like to know if there is, does they share the same focal mechanisms or not?
They are different. I do not do the focal mechanism analysis. This due to we don't want it due to the earthquake occurred. You cannot get that too much information. So yeah, it is correlated, but it includes a lot of uncertainty. Yeah, you need to take the risk. Yeah, you need to use it. You need to take the risk.
Please.
I'm interested about like the written period of the earthquake because like in Taiwan earthquake is like very frequent.
Yeah.
But in my country, in 2010 had a big earthquake. But we never know like when another one will happen. Like you have the system happen to you.
Yeah.
Like in this system, then we have like you get information about the written period of another earthquake.
Another earthquake?
Yeah. For the written period.
No, this is an earthquake detection. This is a focus on the early warning. Yeah, in the past I did some work about the forecasting, but recently, I guess, for my experience, you want to roll down the seismic hazard. The first, you need to build up a good building. Okay, you need to know the site condition, ground condition, build up a good building. But to build up a good building, it takes a lot of the second way we try to do is early morning. Try to have an early morning, maybe set some lights. But for the following the forthcoming earthquake, I guess for prediction, now earthquake prediction is not so mature.
So the system like that will know exactly the location that the earthquake might. Is setting out and you like is it that everyone to know exactly the location that the earthquake will happen? For example, Malian or I don't know, Bhubaushan or Taipei.
Yeah, you mean when after the earthquake occurred?
No,
Before a little bit different. We know, I guess the different ways we try to do is to do the so-called probabilistic seismic hazard analysis. We know the probability, but not exactly.
Time.
The time. We know the probability. So we try to do is just our group of people. We are trying to study the seismicity where we dig the fault. We dig the fault. We dating the different fault event. We know the seismic interval. Then we know the probability, but we do not know exactly when. But we also basically the size also can be expected. This is we can do through the seismic hazard analysis. I guess this is also very important to your country. So this is why I travel a lot of country to about around the last 10 years. I travel a lot of country to have the workshop and the training course to help those countries to set up a early warning system using low-cost sensor. This is to try to do also that we collect the information that can contribute to the seismic hazard analysis.
Yeah, the earthquake is very different from typhoon.
Yeah.
I think some people just we have different ideas of the disaster also based on our experiences. But the earthquake is very so the 5 to 10 seconds is very important already.
Yeah, already
right?
important. Just like the new technology. Just like you have the active control of the building. So it's just a few seconds. You can activate your building to resist the forthcoming shaking. That is very important.
Yeah, the 5 to 10 seconds is enough for you to run away from a building to go outside.
First floor, ground floor, you can go out.
Yeah, please.
Okay, Reza, I have heard a very interesting saying goes, there is no use escaping from the earthquake. It is too big, and you don't have to escape if the earthquake is too small. So, do you think people will escape when they receiving the warning? Because in my opinion, and the friend around me, I haven't seen anyone receiving the earthquake warning and escape.
I can share some experience. Okay. First, you need to find one pier east to your building. I think that for the earthquake, you will need assurance. You are seismometer. Okay, assurance you are detector.
Okay.
So when earthquake occurs, for a moderate or small earthquake, moderate near field earthquake, you will feel the up and down shaking. Then the few seconds, you will feel the horizontal shaking. But this is contains high frequency. It's high frequency. Then you know this is moderate earthquake pretty close to you. So generally you can count down from the initial shaking. You count 1 second, 2 seconds to the horizontal shaking, and multiply the 8. This means the distant earthquake from you. Okay, but today you feel the more distant earthquake. Generally, the moderate to a little bit, not a really big one. It cannot be a little bit harder to feel the up and down shaking. You just feel, hey, yesterday I may not sleep pretty well. Recently in my house, and some why I got a headache. Or this is a moderate earthquake. So you will also can just like a middle distance, the shallow earthquake. Yeah, you will feel the occur. You will feel the up and down shaking, but the up and down may be small, but following the shear wave coming, you will shake a lot, just like a few weeks ago the Hawaiian earthquake. And the really damaged earthquake, just I mentioned, I just show you for really large earthquake, damaged earthquake, you will feel the up and down shaking, but you feel strong and slow. Strong and slow is mean this displacement is high, it's large. Strong, you feel strong, but it's slow. This means the large earthquake P wave. And not only one shaking, it may be up and down for several circles. This means the shallow earthquake. So at that time, yeah, try to find cover where you can escape from the ground floor, you can go up. Otherwise, the following shaking may cause the damage. And in Taiwan, you also can feel the deep earthquake. Deep earthquake, this is a subduction earthquake. So for the subduction earthquake, you will feel the up and down, but maybe just one or two circles. Maybe you will feel very strong, but a little bit disappear. It's due to the seismic wave from deeper packet to here. The most energy concentrated around the first key arrival at that circle. And then feel several seconds, you will feel the ground shaking, horizontal ground shaking again. That could be energy also large, but not as too many circles go down. It's just really a little bit shaking. This is a deeper earthquake. Why the deeper earthquake and with the shallow earthquake, you feel it different? This is due to the deeper earthquake, much more energy concentrated around the key arrival and the S arrival. For the shallow earthquake occurred, you had a multiple refraction from the crossed area, so you feel the up and down shaking, but you still have the so-called cold down wave following. So this is the but generally cause the damage the earthquake may be just a strong shallow earthquake will cause much more damage. This is just as soon you are detected.
So the earthquake is very different from the damage, right? The strong earthquake does not necessarily cause the great damage. Depending on the horizontal.
Yeah, not only the here I just use a peak ground velocity. Peak ground velocity is much easy to cause the damage, but you need to know the shaking. Small shaking, moderate shaking, but the longer time, it also cause the damage, depends on. And really complicated. And it also maybe you have the building, the natural frequency is very close to the seismic wave that the building could be also cause the damage.
Okay. So right now, the one we received the warning from the APP, can they tell us about the P wave or the S wave, and then the horizontal or the vertical, and then we can decide we want to go out or not?
No, they just give the earthquake curve. Yeah.
Okay.
A little bit, maybe estimate the intensity.
Yeah.
They just provide this information. Yeah.
Okay.
Generally, we will not use APP. APP will too slow.
Is it too slow?
Yeah. Due to the few people use app, okay, it's fine. The too many people use app, they will become slow. So I guess you guys have that experience. So now we just use NCC, is using broadcast. There's the information reach the mobile tower, so it's broadcasted to the surrounding the mobile phone. Yes.
But a few weeks ago, the Taiwan Taida also used the broadcasting or no?
No.
Okay, so Taida
Yes,
is try, right?
NCC. But broadcast is now new 4G mobile phone power. They can broadcast. Your mobile phone within the region, you will receive the information. It's an app that is two-way, okay? But the broadcast just one. A little bit different.
Okay, broadcast.
Yeah, broadcast.
Okay. Long way, and then the next step. Long way.
So this broadcast will only tells us like there will be an earthquake, but how big it is, do we know?
They will estimate the intensity, yeah, and the arrival time.
Okay.
It's due to this is the regional one. They already calculate the epicenter and the magnitude. They just convert it to each mobile phone tower.
Okay.
Okay.
I guess maybe the distinct region.
I see. So right now those high-speed roadway or MRT, they will automatically stop. It's due to they feel the shaking or they can receive this NCC broadcast.
Okay. For the high-speed train, they use their own system.
Okay, now that's
But it's really old system. About 30 years ago. But it's also robust, but not dangerous. But it needed to reach the ground shaking, reach some threshold.
Yeah.
They will slow down the train.
Okay.
But they do not use the early warning technology today due to the design of the high-speed train. It's a major design by Mitsubishi Heavy Industry. You want to add this function, they want the Central Bureau to take the responsibility, but there's no way. A little bit, about 20 years ago, I already discussed with some expert about this portion. And the MRT received the Central Bureau information. MRT also have some instrument, but they now just try to replace the user.
Okay. Chris,
So why the earthquake in Hualien in 2017 and this year have such different pattern from PGV from your PowerPoint, and although they have similar magnitude and epicenter?
Okay. Central Bureau first the report, I guess 2 years ago, the Hualien earthquake, they underestimated the magnitude. Actually, it's 6.4. And this year, I guess the 6.1, I guess a little bit, this earthquake could be the 6.1 or 6.0. You know the 0.3 magnitude unit a little bit different. And the damage pattern is due to the 2 years ago, the rupture very close to the surface, so it caused the damage. And this year, the rupture much deeper. The rupture, full rupture do not extend to the surface. Yeah, this is a major reason.
Okay. Now,
I want to repeat the previous question. A few weeks ago, the earthquake, we were having a faculty meeting. The alarm comes up, and the first reaction I
boost the voice from a boost cell phone. And I stop for 3 seconds. The other says one. And I take it out and wait for the C message. It's already 10 seconds passed. So what can I do? So maybe they should give a different siren, different sounds to make you know what kind of magnitude it is, so we can have better reaction.
Yeah, they need to
Right now, we cannot tell the strength.
Yeah, for the warning, for issue the warning only by the, now I guess Central Bureau can issue the warning, and another agency maybe just NCDR also can issue the warning. Other people cannot issue. We only can do is we can install a device, give warning from your device.
So can you suggest and give different siren, like the frequency? High frequency means stronger earthquake.
Yeah, need a design. Even located within the campus. In my office, I install a pillar.
In this office, right? In this building over there.
It detects 60 gales. But in our building, Department of Geoscience, we also install one pillar there. It just detects 6 gales. So you know the difference, almost 10 times within the location, within the campus. It's due to the Department of Geoscience. That area is close to the mountain area. The sediment is not too much sediment. It's close to the bedrock. Here, the sediment is much thicker. And my office is located third floor. So the building effect is amplified. This is why in the Taipei, you feel the shaking is larger and the duration also longer is due to the basin effect. The basin effect is the seismic wave trapped in the basin. And another is in the sediment, you also have the side effect due to the soil the salt. So you have the salt. And multiply you have the high-rise building. So you will feel energy large and the ShakingAlarm. Especially not designed the high-rise building.
Any other questions? Please.
Professor, do you think that it's possible to adapt this technology to other cheaper sensors like our Raspberry Pi?
Okay. Raspberry Pi use geophone. They also have manual geophone, but they connect to their server. Then you can get into it. I don't want to do it. I needed to design our product by ourselves, the signal directly to our server. I don't want the signal through your server. I don't want to use. This is a Raspberry Pi. And still a lot of the chip sensor that need the design. Otherwise, for the main sensor, generally they include a lot of the noise data. They need some technique to remove, to load, not remove, to load down the noise.
Any other questions?
And many people here, they will receive the message when the earthquake strikes, but I never get it. So they say, because I do not have the internet data, so is it through the internet data?
No.
But I really didn't get anything, including the
Maybe change your mobile.
This is a new one.
Maybe your cable company.
Yeah. Generally, your mobile phone will see undercover of the mobile signal. You will receive.
Yeah.
You will receive. This is broadcast.
But even we are outside of Taiwan, so we can't. That is based on the signal from the cable company.
No, that could be an app.
That could be app. Oh, app is different from the signal. Okay.
Yeah, app is different from the broadcast. That is app.
Okay.
If we use Wi-Fi, can we get the broadcast?
Your mobile phone.
Mobile phone is
You have a mobile phone, then you will get the information. It's broadcast. Just like you call the 911 or 119. You no need to have the connection.
So the signal is a telephone signal.
Yeah.
Yeah,
You
rather
have
than
a
Wi-Fi
mobile
thing,
phone can receive the signal. You can receive the one.
Okay.
This is a broadcast.
So 3G or 4G, both can be seen.
Or 4G.
Only
4G. 4G.
About 4G.
4G.
About 4G. Okay.
Yeah. 4G. Due to the 3G, they do not have the channel for broadcast. They have one channel for broadcast.
Okay. Any other questions? Okay, please.
First of all, is there a system to tsunami hazard purposes? How suitable is the system for tsunami hazard purposes?
For tsunami, a little bit difficult for here, but due to you want the tsunami location should be fine, but you want to, could be determine the magnetic, the focal mechanism also very important. So generally for this type of purpose is to provide a shakemap. Shakemap can convert to the size of the earthquake, but now still a little bit need more work to get the focal mechanism.
Maybe. Okay.
General question. Is there any maybe specific reason or research about like why the magnitude of the different earthquake are all the same? Is there any research?
For different earthquakes?
Yeah, for different like the magnitude, for example, 4.5.
Okay.
6, 7.
Yeah, we already have the new product due to the mains is rolled down, and we can use another so-called geophone. Just we have the new product is you use geophone. Geophone is also cheaper, but now the like mains is the mechanical geophone. And now we have a new product. One product is 3-component acceleration and added the one vertical geophone, so you can detect a small to bigger earthquake. That could be used to detect the earthquake and provide seismicity catalog for seismic hazard analysis. We also have another product for 6 channel, but it will increase the cost. We will need to try to find the best point.
Equilibrium, balance. Okay, I might have the one question.
Okay.
About you showed to the end about that kind of the technology has been distributed in many other countries, right?
Yeah.
And at the beginning, I believe that is very good for the social service because we can save the people's lives in other countries. But if all of the data is connected,
it is we promote to their country, but we do not receive their signal due to simply I just training their people to do their job. I do not receive their signal. Simply I just training people. I travel a lot of countries. Simply I just training their people to design their system by themselves. I do not receive their signal. That was a little bit
controversial.
Yeah. I don't want to involve the controversial. Simply we just provide our knowledge, provide our training, training their people. They do their job. They protect their country.
Okay. Any other countries? Questions? Otherwise, we say thank you again for